Hello viewers, welcome back to my channel Shraddha's Physics. In this part, we will see the previous year question of the state selection board exam, that is your SSB physics exam. So in this part, we will basically see the 2021 question, and this is the first part. Here we will discuss only 1 to 5 questions. So let us start with our first question. So the question is, a one-dimensional coupled oscillator, it consists of two identical masses connected to three identical springs. The free ends of the springs are fixed to two parallel walls. It can move on a frictionless horizontal surface. So which of the following statement is true about the motion of the coupled oscillator if it is in a normal mode? So basically the question is, so it is the two coupled oscillator problem. So basically a one-dimensional coupled oscillator, it has the two identical masses. So masses are constant, that is m1 and m2, these are equal to suppose m, and they are connected to three identical springs, and here the free ends of the spring are fixed to the two parallel walls, and it can move on a frictionless horizontal surface. And here for the normal mode, the question is, the options are, the all parts of the oscillator is oscillating sinusoidally with the frequency of mode, or all parts of the oscillator is oscillating with a linear combination of the two frequencies of the normal modes, or one mass oscillates with the frequency of one mode while the other mass oscillates with the frequency of the other mode, or the period of the oscillation is a common period of the two modes. So basically here we will discuss first, in case of the two coupled oscillator, let me write, in case of the two coupled oscillator, so here we will consider there are two masses. So suppose this is my residual and here one is the residual, and here suppose one mass is present here and another mass is, suppose it is placed over here, and it is connected with the three springs. So suppose let us, this one is one and this one is the second spring and this one is suppose the third spring. Okay, and here the mass are same, here the mass is m and also it has the mass m. Okay, and let us consider the spring constant of this two spring. Sorry, here the two spring is k, and here the for the third spring this is suppose k prime. Okay, and this is the y. So this is the basically figure for the two coupled oscillator as you have studied. And if it will oscillate, then suppose the displacement occurred by this mass, this is suppose it is displaced to the position. So let us, it will displace from this position, and also this one, it is displaced from the position, it is originally at this point, so here it is displaced to this position. Okay, now it has also the mass m and it has also the mass m, and this is your residuals. Okay, and here the suppose the displacement is x1 for the first mass, and for the second one from the original position, this is suppose the displacement is your x2. Okay, so the main things, that is the important things that you need to remember in case of the two coupled oscillator, that is the question should be asked from this part basically. So the first one is, each coordinate, it is a superposition of the two simple harmonic motion. Here I am considering for the coordinate. So each coordinate is a, I am considering for the coordinate. Okay, this is the important. Each coordinate is a superposition of two simple harmonic motion of frequency omega 1 equal to omega naught, and omega 2 will be equal to omega naught square plus 2 omega c square whole root over. Okay, then what is this omega naught? So this omega naught is the two oscillators when that is the angular frequencies of the two oscillators, when they are not connected, each vibrate with this frequency. That is when the in between these two masses, when there is no spring, we can say they will oscillate with the frequency omega naught, that is each will oscillate with the frequency omega naught when they are not connected. Okay, that is your omega naught. Now the next important thing is for the normal mode. So for the normal mode, these are the important points, so you should note it. For the normal mode of vibration, normal mode means the displacement of any mass, it is the linear combination or the superposition of the two modes. That is x1 and x2. That is, if I let me write, the normal mode means the displacement of any mass, the displacement of any mass is a linear combination of, this is the displacement, okay, is the linear combination of superposition of two modes, that is x1 and x2, capital X1 and capital X2 oscillating simultaneously. I will tell you what is capital X1 and capital X2 simultaneously. So here small x1 and small x2, they represent the displacement for the mass m1 for the two different masses, that is m and m. So here if I consider these are the masses m1 and m2, so that here the displacement will be x1 and x2, but since here we are considering they have the same mass, so here basically, so the displacement are x1 and x2, this is your small x1 and small x2. So here this capital X1 plus x2, this is your small x1, is equal to capital X1 plus capital X2, and small x2 will be equal to x1 minus x2. That is basically, if we will say the two masses, that is these two masses 1 and 2, these two masses, they can move in the same direction or they can move in the opposite direction. So depending on that, we can write here. So the normal modes can be categorized into the two types. One is the symmetric mode and another one is anti-symmetric mode. So for the symmetric mode, so both masses have equal displacements. They have equal displacements. And have the same frequency. Okay. Same frequency, and that is omega 1 equal to k by m whole root over. This is for the symmetric mode, that is when they have the equal displacement and we can say they are in phase. Okay, they are in phase. So here x1 can be treated as equal to x2, that is plus x2. So here x1 equal to x2 and they vibrate as no coupling between them. Okay, so they vibrate as no coupling between them. And similarly, if I will consider for the anti-symmetric mode, let me write for the anti-symmetric mode, these are your important points. So for the anti-symmetric mode, both the masses, they have equal and opposite displacement. Okay, both masses have equal and opposite displacement. But they oscillates with the same frequency. So same frequency means here in case of the anti-symmetric mode also, so the both mass have the frequency omega 2 equal to k plus 2k prime divided by m whole root over. Okay, and you know k is the spring constant, and here they are out of phase. Out of phase means here the coupling is working here. If I can write here, the coupling is working. That means they will couple. Coupling is working. So here in our question, you have to calculate. So the option is, if it is in a normal mode, you can see from this option, all the parts of the oscillator oscillating sinusoidally with the frequency of the mode. So this one is our correct answer. That is, here you can see the frequency is here in case of the two coupled oscillator, whether it is in symmetric mode or in case of the anti-symmetric mode, they always have the same frequency. And so here the answer will be all the parts of the oscillator, it is oscillating sinusoidally with the frequency of the mode. And one important thing is the two coupled oscillator example is, if I will give an example, that is two coupled pendulum. So this is the example of two coupled oscillator. Okay, so let us consider this is your rigid support here, and here the pendulum, this is the, suppose the mean position here, and it is oscillates to this point, suppose here first, and here the, for the second one, let me draw clearly. So for the, this is the mean position, and here the pendulum position. Okay, this is the pendulum position, and here it is attached with a spring. Let us say it is attached with a spring. So here the displacement from the mean position, it is suppose x1, and here suppose x2. Okay, and in the other condition maybe like this is suppose the rigid support here, and here again the mean position. Let me change the color so that it will be clear to you. So this is the mean position, and here also the mean position of the pendulum. So it is, if the pendulum is displaced to this position, so let us say to this point, and here also at this point, and here it is attached with a spring like this, and the displacement from this point is x2. This is x2 point, and here the displacement is your x1. Okay, so now in this case for the two coupled pendulum, you can see omega 1 equal to g by L root over, this is direct formula you can remember, that is here when x1 equal to x2, it means that when they are in same phase, so the frequency will be equal to omega 1 will be equal to g by L root over. But when x1 equal to minus x2, that is there out of phase, when it is out of phase, so in that condition you can write omega 2, that will be equal to z by L plus 2k by m whole root over. Okay, so this is the important thing you should remember for the two coupled pendulum, which is the application of the two coupled oscillator, you may say. This is the example of this. So omega 1 will be equal to z by L root over when x1 equal to x2, that is they are in same phase, and omega 2 will be equal to z by L plus 2k by m when x1 is not equal to minus x2, that is they are in opposite direction, so that is called out of phase. So you can see here when x1 is in this direction, when x1 is in this direction, so x2 will be just opposite to that x1. Okay, so here x1 equal to minus x2, that is out of phase, but here the x1 as well as x2, they are in the same direction. Okay, it may be in this direction, or maybe x1 and x2 they both in the left side direction. Okay, that is called the same phase. So for the same phase, omega 1 will be equal to z by L root over. Now let us see the next question. So the next question is, there are three vectors, that is a, b and c. They are defined as a vector equal to xi cap minus yj cap plus zk cap, and b vector equal to xi cap plus yj cap minus 2j cap, and c vector equal to xi cap minus yj cap plus k cap. Then which of the following statement is true? So you have to basically, in the option you can see a and b both may represent magnetic field, b and c both may represent magnetic field, a and c both may represent the magnetic field, a, b, c all may represent the magnetic field. Now here you have to find whether a vector or b vector or c vector, they represent a magnetic field. Okay, so first of all, to solve this you should note that, so to check whether the vector is a magnetic field or not, so the Maxwell's equation del dot b equal to 0 you have to basically check. Okay, so now you know del vector equal to I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z dot. In place of b vector, let me write first a vector, that is you have to check whether a vector, b vector or c vector are magnetic field or not. So if I'll put the a vector value directly, that is xi cap minus yj cap plus zk cap. Okay, now that is equal to, you know, I dot I, z dot j and k dot k, these all values are 1, and all I dot j dot k, these values goes to 0. Okay, so here I dot I, so that will give your 1. So dou by dou x of x, that is your 1, plus j dot j is your 1. So dou by dou y of minus y, that is your minus 1, plus k dot k is your 1. Dou z by dou z will be equal to 1. So here you can see the answer is 1. So a vector is not a, it will not give a magnetic field. So it is not a magnetic field. So the first option is not our answer, and also C and D are eliminated. So directly you can check your B answer is the correct. But let me check here for the B vector and C vector as well. So now for the B vector, if I will directly put, let me erase this part, directly I will write here. So in this part, if I will write, the B vector value is xi cap plus yj cap minus 2zk cap. This is 2zk cap. Then this is equal to I dot I is your 1, dou x by dou x is 1, plus j dot j is 1, dou by dou y of y, that is also 1, k dot k is 1, dou by dou z of minus 2z will be minus 2. So 1 plus 1 minus 2, that is your 2 minus 2 is 0. So this B vector will give a magnetic field. So this one is correct. Now here we will check for the C vector. Now let me erase again. So now for the C vector, if I will check, C vector equal to xi cap minus yj cap plus k cap, and here the dot is present, that is equal to I dot I is 1, dou x by dou x is 1, plus. So let me write z dot j is 1, dou by dou y of y will be minus 1, and again plus k cap dot k cap, that is 1, and since here 1 is present, so dou by dou z of 1 is 0. So this is plus 0. 1 minus 1 is 0. So here we concluded that, here we have concluded that del dot, just a minute, del dot A is not equal to 0, but del dot B and del dot C, they will give your 0 result. So here the answer will be B and C vector, both will represent a magnetic field. Okay. Now let us see the next question. So here a particle of mass m equal to 0.1 kg, it is initially motionless on a frictionless surface. Okay. At time t equal to 0, an impulse is imparted to the block and it starts moving on the surface with a uniform acceleration a equal to 10 meter per second square. So what is the action? What is the action of the particle at time t equal to 1 second? So basically you can see here the time is fixed. Okay. So time t equal to 1 second is given. So for that time you have to calculate the action. So first of all you will write action. How you can calculate? Action equal to simply force into distance into time. This is your action, force into distance into time. Okay. So now the mass is given and for this time you have to calculate, and here the acceleration is given. You know force equal to mass into acceleration. So here mass equal to 0.1 kg into acceleration is 10 meter per second square, that is equal to 1 by 10 into 10, that is basically 1. So here the force equal to 1, that is Newton. So here I have calculated force equal to 1. Now the distance you have to calculate. So for the distance, you know S equal to ut plus half at square. S equal to ut plus half at square. So from this question you can see initially it is motionless on a frictionless surface. Okay. So initially it is at rest and it starts moving on the surface with a uniform acceleration. So basically u is 0 here, plus 1 by 2, acceleration is given 10 into t square means 1 square, because for the time t equal to 1 second, this is 1 square. So 10 by 2 is basically 5. So this is the distance. Okay. Now 1 into 5, 5 is the distance into time for 1 second you have to calculate. So here from this question you can see for the 1 second time you have to calculate. So here 5 into 1 into 1, that is equal to 5. So the action will be equal to 5. So the value here is 5. So this is our correct answer. In this way you can solve this question. The next question is, a particle of mass m and angular momentum L is moving in an attractive potential U of r equal to minus alpha by r square. Where alpha is a positive constant of appropriate dimensions, it may reach the center of force due to the potential U of r if the options are alpha less than minus L square by 2m, alpha equal to minus L square by 2m, or alpha greater than minus L square by 2m, or alpha is less than minus L square by m. So here when a particle is under central force, the total energy E can be written as equal to 1 by 2 mr dot square plus 1 by 2 L square divided by mr square plus the potential V of r. Okay, and here this is known as your V effective, that is your effective potential. This total is known as the effective potential. Okay, so the condition for the stability in radial motion, you have to put d square V effective divided by dr square. It should be greater than 0 at r equal to r naught. So this is the basic condition to check for the stability. And also you should note that E should be greater or equal to VE of r. So here you can see in place of L square by 2mr, in this part L square by 2mr square, here the term is minus alpha by r square. So basically this is your alpha, if you will consider that to be alpha. So this is L square by 2m, this part is your L square by 2m. So you have to check whether alpha is related to the L square by 2m or not. So in this all three options, this is L square by 2m is given. So D is not the answer. Okay. Now here this minus L square by 2m to be considered because alpha is a positive constant. And also E is greater or equal to VE of r. So here the answer will be alpha should be greater than minus L square by 2m. Okay, this is our correct answer. Now let us see the next question. At time t, the two electric charges are at a distance r. The distance between them is r prime at time t prime. The equation of motion allows a series of similar paths. If t prime by t equal to r prime by r power beta, then beta equal to, t square is proportional to the r cube. Square of the time period is cube of the semi-major axis from the Kepler's law. So if you will apply that, so this t prime by t whole square, that will be proportional to r prime by r whole cube we can write. Or simply if I will divide 1 by 2 in the power, then this will be t prime by t will be proportional to r prime by r. This is whole power 3 by 2. So here this 3 by 2 is nothing but beta. So here our answer will be 3 by 2. Okay. So this is all for today. These are your total 5 questions here we have solved, and in the next part we will solve some more questions on this 2021 previous year question. This is all for today. Thank you all.